Okay, so so what we're going to do is we're going to find the flow rate for this last problem. And again, I'm going to call it Q, but the book, some of the problem books call it J. The PDF textbook calls it Q. I'm kind of more accustomed to Q. So I want to make sure my units match up. So I don't want the radius to be in inches. So my radius is 3 inches, and I'm going to convert that. 1 inch is equal to 2.54 centimeters. So that is 7.62 centimeters, or even better, we can make it meters, 0.0762 meters. So my flow rate is pi times 0.0762 squared times 1 meter per second. So these are meters. When I multiply by a meter per second, I'm going to get meters cubed per second. And what I get is 0.018 meters cubed per second. And I'd like to go ahead and convert that into liters, both for practice, but also to get a sort of a sense that makes, in units that are easier to visualize. So I know that 1 cubic meter is 1,000 liters. And, conversion factors like that will, of course, be on your equation sheet. So that's going to be about 18 liters per second. That's actually quite a hefty flow of liquid. All right, any questions about that? Okay, now I want to do another poll. Give me a second to set it up. Okay, I want to talk about this system, and I want to know where the higher pressure is. Is it higher pressure when the water comes in, over here, kind of where we have V1, or is the higher pressure where it comes out, over here where we have V2? So just tell me what you think. You don't have to be right, but just make your guess. Higher pressure at point 1 or at point 2, in or out? So I'm getting 6 responses here, and 0 responses there, and 3 no responses, one of which is me. So okay, it's pretty universal. Everybody believes that the higher pressure, wait a second, did I get that? I got it wrong. It's 6 on the, say it's higher pressure here where the water flows out, and 0, say it is higher pressure on the inlet side. So good, everybody is unanimously wrong, because this is the high pressure and this is the low pressure. But that's okay, you're in company. Virtually everybody always thinks of this in the wrong way. So let's see if we can kind of get a grip on it. What I'm saying, you guys know this water hose, this is a fire hose. It's spraying out this, super powerful stream of water that's moving, 48 meters per second, dumping 18 liters of water, which is, more than 4 gallons of water per second. Okay, that is the low pressure end of the tube. And back here, where the water is moving sluggishly, just 1 meter per second, that's the high pressure. So first of all, a couple of things. When the water starts going out into the air, the pressure is 1 atmosphere. That's the pressure at this location. The water's coming out into 1 atmosphere, and it becomes pressured at 1 atmosphere. The pressure back here must be greater than 1 atmosphere, or the water will flow the other way. Okay, if the pressure inside the tube is less than 1 atmosphere, then the atmospheric pressure is going to push water the opposite way. So the water is always going to flow from the high pressure location to the low pressure location. But I would say, almost universally, have the wrong idea about this, because when we see this super fast stream of water coming out, we call that a high pressure stream. But what it really is it's a stream of water with high velocity. But how does it get to be such a high-powered, high-velocity stream? Well, it's because we must have had high pressure back in the tube somewhere. And the higher the pressure is back in this tube, the faster the water is going to come out when it gets down to 1 atmosphere of pressure. Okay, there's a lot of phenomena that I can point to illustrate this point, that the faster the fluid moves, the lower the pressure. Let me just write that. Faster fluid means lower pressure. Okay, the faster fluid is happening when the pressure is lower. So just think about driving in the car, and you're on the highway, you roll down the windows. I don't know why you would roll down the windows on the highway, but maybe your air conditioning doesn't work. And all of a sudden, there's like a little wrapper or something, and it just goes out the window. Raise your hand if you ever had that experience. Only 3 people, 4 people, the rest of you keep your cars spick and span. Okay. Now raise your hand how many times you're driving on the highway with the windows open and a wrapper blows into your window. Okay, how about how often, you have the windows down, you're driving, and bugs are flying in, just swarms of bugs are flying into your car when you're on the highway. Raise your hand if you've hit bugs on the highway. Just they hit your windshield. Okay, how come they never come into the car? You can drive through a swarm of locusts, full speed, going 70, 75 miles per hour on the highway with your windows down, and you probably won't get a single one of those things in your car. If you do, it's very, very lucky. Why is that? It's because the pressure inside the car, where the air is not moving as fast, is much higher than the pressure outside. This is why if you roll down the window, a piece of paper or something can just flies out of the window. If you have long hair, your hair will fly out of the window. When you try to roll it up, your hair gets caught in the window. Raise your hand if you have that experience. Okay, I've had that experience. So, that's all because there's higher pressure inside the cabin of the car than outside. And that's because the velocity outside is much higher. If you're driving 70, 75 miles per hour, the wind as it goes past your car is like 70, 75 miles per hour. Other places where we might see this, you might, on a windy day, you might see your curtains get sucked up against the window. Raise your hand if you ever saw that happen. Curtains just get sucked up against the window on a windy day. So the wind does not blow the curtains into the room unless you have a window open on the other side or a door open. If you've got doors or things open on each side of the house, then air can start blowing through. Okay, but if you just have a single window open, even if it's windy outside, the wind can't really blow into the house because the house is already full. And what instead happens is as that fast wind moves by your house, it creates low pressure, and that will sort of suck things out. That's why you open the window when you burn stuff in the kitchen. Not that I burn stuff all the time, but it happens from time to time, and you open a window. But if you just open one window, it's not as good as opening windows on opposite sides, because then wind can actually blow through. So where else could you see this? So in sports, this isn't really a great illustration, but in sports, if you have a ball and the ball is spinning, okay, so this could be baseball, throwing a ball and putting a spin on it, making a curve ball. It could be soccer, bending a soccer ball. It could be golf. You slice the golf ball. You don't hit it in the center, so the ball gets a spin on it. And when it spins, what happens? It drags air around with it. And then it's going into, if the velocity of the ball is taking it into sort of the wind or into just the still air, one side of the ball has a greater relative velocity than the other side. And so what happens is you get low pressure on one side and high pressure on the other side, and the ball will bend. So there's lots and lots of examples of this. Now, I don't want to go through the physics equations that will kind of confirm this today, because it's kind of a long story. It's pretty complicated, and that's really what's planned for tomorrow. But I want us to keep in mind today that the high velocity means low pressure, and low velocity means high pressure, which is exactly 180 degrees, totally flipped from how we all think about it. Okay, any questions? Okay, so so the last thing for today, and you might be getting a sense that this chapter on fluids is really like kind of a miscellany. It's a little bit of this, a little bit of that, some stuff about pressure and depth, some stuff about how fast the fluid moves when it goes, from one tube to another tube, and that's very much, tomorrow we're going to talk about how that affects the pressure. We're kind of hitting all of these little points, and they're not always totally connected other than just that they all involve fluids. But we're going to talk today, our last topic for today is about Archimedes' principle. Okay, raise your hand if you ever heard of Archimedes. Okay, and I don't count it as heard of Archimedes if you're just talking about the owl and the sword and the stone. So anyone want to take their hand back? Okay, good. So who can tell me who Archimedes was? Don't just say some old Greek guy. Okay, Archimedes was an old Greek guy. No, actually, he was not Greek. He was Sicilian. He lived in the city of Syracuse, which is on Sicily, and he was a very influential person in his day in a lot of ways. So we're going to talk about his principle in a minute, but just a little background on him. He was very good building machines. He understood the principle of the lever very well, and so he wound up in his time building a lot of war machines that would defend the city of Syracuse, because this was at the time when the Roman Empire, the Romans were really starting to try to expand and conquer everybody. And they would come to Syracuse every year and try to take the city. It was a very prosperous city. It was a Greek trading colony. That's why he has a Greek sounding name. But by this time, it had been its own place for some time. And he built, some kind of catapult that when the Romans would try to come by land and take the city, even though they had some kind of catapult of their own, he had just a much better catapult. And so he could just demolish them before they would get close enough to the city with their own catapults. So they weren't able to breach the walls of the city. They tried to come by sea because it was a port city, and you have to take these stories with a grain of salt, because the stories come from the Roman soldiers who were kind of going back in defeat and trying to explain why the mighty, their mighty army couldn't take this little city. But they said that that there was some kind of a giant claw that would come out. I'm just gonna turn off the whiteboard for a second. So they said there was a claw that would come out and it would just grab their ships and pick them up and smash them on the rocks. So they basically thought that Archimedes was some kind of a wizard. And modern people trying to understand this have suggested that what Archimedes made was a crane. And he just made a crane, and it would sort of come out over the water and drop down a hook, which probably was made to look like a claw to scare people. And they would pick up the ships and then take them and drop them on the rocks. So the Romans couldn't take the city by land. They couldn't take it by sea. And this is primarily because of all of these machines of war that Archimedes created. And so they did eventually take the city, though. Anyone have a guess how they got in, if they couldn't take it by land or sea? Don't say air. Don't say it. Wasn't air. No airplanes in that time. So they bribed the guards at the city gates, gave them some gold, got them to open the gates, and then they came in and took the city. So when they went in, they, the general, who was very proud that he was finally the one who cracked the city, he told one of his soldiers, go bring me Archimedes. And by the way, Archimedes was not the king of Syracuse. He was just like their resident, intellectual. But the king was the general was very excited to get his hands on Archimedes, because once they got Archimedes, they could start enlisting his aid to build machines to destroy cities instead of defending them. And so the story goes that the soldier went to Archimedes. He found Archimedes basically in his lab, the equivalent of his lab. And he said, Archimedes, come, General Scipio demands it. Archimedes' response was, not right now, I'm busy. And so the soldier took out a sword and he killed Archimedes on the spot. So that was the end of Archimedes. And my strong suspicion it was the end of the soldier too, because the soldier wasn't that important to the general, but Archimedes was really important. And if they had gotten their hands on Archimedes, we would probably all be speaking Italian right now. But they didn't get Archimedes, and so they just had to conquer the world in the old-fashioned way. Anyway, why we're talking about Archimedes is coming from a little bit earlier, before his ignoble demise. The king of Syracuse, a guy named Huron II, had basically, he was feeling pretty proud of himself for fighting off the Romans all these years, and so he took a big block of gold and he gave it to this goldsmith, the best goldsmith in Syracuse. And he said, I want you to make me, the most magnificent crown anyone has ever seen, something that will embarrass Caesar, just a mighty crown. And so the goldsmith took the gold He made the crown. He gave back the king this fancy crown. But what the goldsmith didn't realize was that the king was paranoid, and he got it into his head somehow that the goldsmith had cheated him, that he had taken some cheap metal and mixed it in with the crown and kept some gold for himself. And it just started nagging at him and driving it, just started just burning away at him. He was convinced that this was the case, so he went to Archimedes and he said, Archimedes, you have got to help me. This goldsmith, he's a crook, he's a cheat. I can just see in the look of his eyes, he's laughing at me. He has stolen from me. You need to tell if this crown is pure gold or not. And Archimedes' response, his initial response was, I have no idea. I'm not a metals guy. I build catapults and stuff. That's not I don't understand that stuff. I'm not an expert in metals. And the king said, well, listen, you are the smartest person on the earth. You're the guy. So you tell me if this crown is real gold, pure gold, within 48 hours, 2 days, or I'm going to cut off your head. So Archimedes, okay, he's got like this deadline, and I keep meaning to look up whether the word deadline comes from the story, because this is like a literal deadline. If he doesn't say, yes or no within 2 days, within his deadline, he's dead. So, but he has no idea. He really doesn't know anything about this. And so the story, and who knows if the story is how much there is in the story, but the story goes that he tried to relax himself and try to figure this out. He went to the bathhouse and he went to take a bath. And when he got in the bath, I'm going to put the whiteboard up again to try to illustrate this. So when he gets in the bath, their baths were more like a swimming pool, but I'm just kind of illustrating it in a way that makes more sense now. So here we go. We've got this bathtub, and it's full of water. Oh, it's full of water. Why is it not filling properly? Okay, it's full of water. And now he gets in the bath, and when he gets in the bath, okay, so he gets in, and his body, it displaces some water. So some water comes overflowing based on essentially the volume, that his body occupies. And as soon as this happens, he jumps out of the bath. It hits him like, the spark of inspiration hits him, and he jumps out and starts running naked through the streets of Syracuse. And this story is so just traumatic to think about that it's stuck with me forever. This old naked guy running through the streets yelling, "Hey Eureka! Hey Eureka!" which in Greek looks like that, but in English looks like this, Eureka. It's literally Greek for "I have found it." And he had found something. He made a discovery in that moment. And he goes back to the king with this discovery. Now, modern, I'm going to tell you what the discovery is in just a minute, but modern people have tried to replicate this experiment using sort of the quality of weights and measures and things he would have had at his disposal, and have determined that it's unlikely that with his principle he would have been able to tell if the crown was real gold or not. However, my personal theory is that he was no dummy, and he knew that this goldsmith was dead. He was going to die no matter what. And if Archimedes sided with the goldsmith, then the king would just decide that Archimedes was in on the, on the crime. And so he just saved himself and said, great and wise king, you're so smart. You have found him out. He is a thief and a crook. How wise you are. And, Goldsmith dies, and Archimedes lives to die another day. But here's what his principle was. he gets in and he sees all of this water coming out. And he reasons that, the amount of water that comes out, the volume of water would be the same as the volume of the part of his body that's submerged. This drawing is the worst drawing I've ever done in my life, so I'm just going to get rid of it. And he decides that, the volume of water was somehow related to the fact that when you're in the water, you feel lighter. In a sense, he was predicting or preceding Newton's third law by a couple thousand years. He reasoned that when you get in the water, you feel lighter because there is a buoyant force. So buoyant means, buoyancy is the effect of floating. When you have something in water or in a fluid of some sort, there is a force coming from the displacement of the water. Again, this is Newton's third law, that if you push 50 pounds of water out of the way, the water must push you with the 50-pound force also. So he reasoned that this buoyant force must be equal to the weight of the displaced fluid. Okay, the weight of the displaced fluid. So as I said, if his body displaces or pushes out of the way 50 pounds of water, then he feels 50 pounds lighter. So in more modern terms, we would say that this is the mass of the fluid times G, or even instead of mass, we would say the density of the fluid times the volume submerged times G. So it's not the whole volume of Archimedes himself, but just the part of his body that is submerged. Of course, you could submerge the entire body, and then the V submerged would be the total volume. So how did this really do him any good? How did it help him? Well, basically, it comes down to this. It gives him a way to determine the density of the crown. If you have a block of gold and you melt it down and you make it into a perfect cube, then you can find the density pretty easily because you can calculate the volume and you can weigh it, and you've got the mass and the volume. But if it's an intricate shape like a crown, in modern times we have these really nice graduated cylinders in chemistry class where we can put something in there and we see how many milliliters the water level rises, and we use fluid displacement to calculate volume. But they didn't have really good graduated cylinders or anything like that. So this is a way around that technical problem. So the idea is as follows. You take the crown and you hang it from a piece of string. Okay, and you just place that piece of string underneath a balance, and you see, how many little weights do you have to do to form a balance. So in modern terms, we would say that there is a tension in the string, and that's the same as the tension on the top of the string. And that tension would just have to be equal to the force of gravity. And that, because of the way the balance works, there's a force of gravity acting on our weights. And the force of gravity on the weights on the right-hand side is the same as the tension on the left-hand side if we get a balance. And that tension is the same as the force of gravity of the crown. And so we could say that the mass of the crown is equal to whatever we put here. Then we submerge the crown in water. When we do that, there is going to be an additional buoyant force, an additional force acting on the crown. And so the tension is going to go down. And when the tension goes down, then the force of gravity that we need up here goes down. Maybe we only need two weights. So let's work with the equation and see what happens. If we take the buoyant force divided by the force of gravity, the buoyant force would be the density of the fluid times the volume submerged times g. And the force of gravity would just be the density of the object times volume, the total volume times g. But because the crown is totally submerged, the g's cancel, and the volume submerged is just the whole volume. And what we find is that the ratio of the buoyant force over the force of gravity is the same as the ratio of the densities. So how do we find the buoyant force? We just look at the difference between the original force of gravity and the new force of gravity. So, or alternatively, we put a pour spout here so that when we drop the crown in, some water flows out, and we capture that water in a cup and weigh it. So there's different ways we can find the buoyant force. And this allows sort of canceling out the volume and finding the density of the object, which would just be the force of gravity times the density of fluid over the buoyant force. And ultimately, the force of gravity would be the density, well, let's just say the mass of the object times g, and the buoyant force is the mass of the water times g. And at the end of the day, the g's cancel out. And so the density of the object would be equal just to the density of water times the ratio of the mass of the object over the mass of the water that it displaces. That's kind of how it works. Now, don't think of this as an equation to memorize, but instead think about this process. Any questions? Okay, so let's try a problem. Okay, this is college physics problem 13.14. Sorry, 1.5. It says, using a scale, a piece of alloy has a measured mass of 86 grams in the air, so that's the mass of the object, and 73 when immersed in water. So the mass in water equals 73 grams. That would be, if we go back to this picture, when we don't have the water, we used 86 grams to get a balance. When we have the water, it only takes 73. And so the difference between those two is the mass of the water. That's going to be just 13 grams, according to Archimedes' principle. And it says, find its volume and its density. So the mass of the water is going to be the density of water times the volume of the object. So we know the mass of the water and we know the density of water, we can find the volume. That's just 13 grams over 1 gram per cubic centimeter. So I'm doing the density of water in grams per cubic centimeter, and so we get 13 cubic centimeters for the volume. Now we can find the density of the object by just taking the mass of the object over the volume of the object. The mass of the object is 86 grams and the volume is 13 cubic centimeters. And that is 6.6 grams per centimeter cubed. I like to write grams GM sometimes because I don't like to confuse it with the acceleration due to gravity. So how does this relate to Archimedes' principle? Well, it's the assumption that the difference in the weight in air versus in water is exactly the same as the mass of that water, which then allows us essentially to find the volume. Now, we could also just solve this the way we did here. The density of the object is the density of water times the mass of the object over the mass of the water. So that would be equal to, let me put this again here. We'd have 1,000 times 86 over 13, and that's 6.6 kilograms per cubic meter. So if we did it that way in kilograms, using density in kilograms per cubic meter, we get, 6.6 should say times 10 to the third. Kilograms per cubic meter. Or these are equivalent units. 6.6 times 10 to the third kilograms per cubic meter, or only 6.6 grams per cubic centimeter. Okay, any questions? All right, so for tonight's homework, you've got basically 3 kinds of problems. You have problems relating the pressure to the depth. You have problems relating the velocity to changes in areas. And then you have some problems relating to buoyant force and Archimedes' principle. Tomorrow, we have essentially one topic left, which is to try to connect everything, find out how the pressure and depth and volume, or velocity rather, are all interconnected, and then just do some more practice problems. So that's it for today. If you have questions remaining, you can stick around. Otherwise, I will see you tomorrow.